Welcome back. Today we discuss thermodynamic relations. Here first we discuss thermodynamic functions. The functions of the state variables pressure, volume, temperature and entropy along with the two relations delta Q equal to du plus Pdv and delta Q equal to Tds enable us a complete knowledge of a state of a system to be obtained. Such functions are called thermodynamic functions or potentials. Change of variables known as legendary differential transformations yield functions that are fundamentally important in thermodynamics. Suppose the state of a system is described by a function of two variables f of x comma y which satisfies the equation df is equal to u dx plus v dy. To change the description to one involving a new function g of u comma v, define the legendary transform g of u comma v as g is equal to f minus ux. Consider the first law of thermodynamics for a hydrostatic system. Here du equal to Tds minus Pdv. Here we define a new characteristic function called enthalpy. Here enthalpy is denoted as H. H is equal to U plus PV. Here U is the internal energy function, P stands for pressure, V stands for volume. Change in enthalpy that take place when a system undergoes an infinitesimal process from an initial equilibrium state to a final equilibrium state is given as dH is equal to du plus Pdv plus Vdp. Here the function enthalpy is given as H is equal to U plus Pv. Difference in the function enthalpy dH is given as dH is equal to du plus Pdv plus Vdp. Here applying first law of thermodynamics, from first law of thermodynamics we get delta Q is equal to du plus Pdv. Substitute this du plus Pdv in the above equation, we get dH is equal to delta Q plus Vdp. Divided this equation by dt, dH by dt, delta Q by dt by Vdp by dt, we get dH by dt is equal to delta Q by dt plus Vdp by dt. Then at a constant pressure this equation becomes dou H by dou T at constant P is equal to delta Q by dt at constant pressure, which is equal to Cp, where Cp is the specific heat of gas at constant pressure. Specific heat of gas at constant pressure. Thus, change in enthalpy during an isobaric process is equal to the heat that transferred. The so-called latent heat measured during a phase transition at constant pressure is simply the change of enthalpy. If a pure substance undergoes an infinitesimal reversible process, here the change in enthalpy function is given as dH is equal to Tds plus Vdp. Here at constant pressure, dou H by dou S at constant pressure is equal to T temperature. Here dou H by dou P at constant entropy is given as V. Here we take at constant entropy and at constant pressure. Constant entropy, this will become 0. Then the equation will become dou H by dou P at constant S is equal to V. Then at constant pressure, this will become 0. Then the equation makes dH is equal to Tds. Then dou H by dou S at constant P is equal to temperature. Enthalpy is a convenient function for problem involving heat quantities such as heat capacities, latent heats and heat of reactions when pressure is the variable being controlled. The next thermodynamic function is the Helmholtz function. It is also known as Helmholtz free energy and it is denoted as F. The Helmholtz function or Helmholtz free energy is generated by a legendary transformation of du is equal to TdS minus PdV. Hence, the Helmholtz function F is equal to U minus Ts. For an infinitesimal reversible process, F is equal to U minus Ts. The change in Helmholtz function dF is given as dF is equal to du minus Tds minus S dt. Here F is equal to U minus Ts, dF is equal to du change in internal energy minus T kept constant change in entropy minus S kept constant change in temperature. dF is equal to du minus Tds minus S dt. From the first law of thermodynamics, we already get Tds is equal to du plus Pdv. Substituting here, du is equal to Tds minus Pdv. Here we get dF is equal to Tds minus Pdv minus Tds minus S dt, cancelling Tds Tds, dF is equal to minus Pdv minus S dt or minus S dt minus Pdv. Here change in temperature, change in Pdv, change in volume. Hence, for a reversible isothermal process means temperature remains constant. Hence, this term becomes 0. Temperature remains constant, there will be no change in temperature, dt becomes 0. Hence, dF is equal to minus Pdv. Then integrating this function, we get change in Helmholtz function final state to initial state is equal to minus of integral I to F. Here I represent initial state, F represent final state, Pdv. Here Pdv is the external work done or work done on the system. For a reversible isothermal isochoric process, isothermal temperature remains constant, this will become 0. Isochoric process means volume remains constant, this will become 0. Hence, dF is equal to 0, F is constant. There will be no change in Helmholtz function, that means Helmholtz function remains constant during a reversible isothermal isochoric process. And importance of this Helmholtz function lies in the fact that it mainly involves in the chemical reactions that take place under isothermal and isochoric conditions, and it is also very much useful in statistical mechanics in the case of partition functions. Okay. Next thermodynamic function is the Gibbs function, and it is also known as Gibbs free energy, and it is denoted as G, and it is generated by a legendary transformation of dH is equal to Tds plus Vdp. Here by applying legendary transformation, we get G is equal to H minus Ts. Then change in Gibbs free energy is given as dG is equal to dH, change in enthalpy minus T kept constant, change in entropy minus when entropy kept constant and then change in temperature minus S dt. Then applying this equation, here change in enthalpy dH is equal to TdS plus VdP. Applying this equation in the above equation, we get TdS plus VdP minus TdS. Here dH is equal to TdS plus VdP. Apply this equation in this TdS minus SdT. Here TdS cancel. Equation will become VdP minus SdT. Here dG is equal to minus SdT plus VdP. So, this Gibbs function is important in the case of isothermal and isobaric process. So, from this equation we get which chemical reaction is important in the case of Gibbs function. Here from this equation it is very clear, it is a function of temperature and pressure. So, isothermal and isobaric process is here. So, for a reversible isothermal isobaric process, this will become 0, this will become 0 because there will be no change in temperature, there will be no change in pressure. So, dG is equal to 0, that is Gibbs function, change in Gibbs function is equal to 0, Gibbs function remains constant. So, connection with process involving a change of phase, Gibbs function is required. Sublimation, fusion and vaporization take place isothermally and isobarically. Hence, during such process, the Gibbs function of the system remains constant. Next we comes a famous mathematical relation. If a relation exists among x, y and z, then z can be expressed as a function of x and y. That is, z can be expressed as a function of x and y. Then we can write the differential of z dz is equal to partial derivative of z with respect to x keeping y constant, that is dou z by dou x at y making constant into dx plus then partial differentiation of z with respect to y keeping x constant, that is dou z by dou y with x constant dy. Then dz is equal to dou z by dou x at constant y into dx plus dou z by dou y at constant x into dy. Then replace this function as m is equal to dou z by dou x at constant y. Then replace this as n. Then we get dz is equal to m dx plus n dy, where z, m and n are all functions of x and y. Then partially differentiating this function m with respect to y, then we can partially differentiate m with respect to y, we get dou m divided by dou y at constant x. Partially differentiating m with respect to y at constant x. Then partially differentiating this dou z, here second differentiation dou square z by dou x dou y get. Then similarly partially differentiating n with respect to x keeping y constant, we get dou n by dou x at constant y is equal to second derivation dou square z by dou y already there, then with respect to x dou x. Then this right hand side of the equation are equal, that means dou m by dou y at constant x is equal to dou n by dou x at constant y. This is known as condition for an exact differential. Here comes the Maxwell's relations. Properties of a pure substance are conveniently represented in terms of four functions. First one internal energy, second enthalpy, third Helmholtz function and fourth Gibbs function. And Maxwell's relations are very useful because they provide relationship between measurable quantities. Then any one of the 8 quantities, pressure, volume, temperature, entropy, internal energy, enthalpy, Helmholtz function and Gibbs function may be expressed as a function of any other two. Consider a hydrostatic system undergoing an infinitesimal reversible process from one equilibrium state to another. Here, first one, when the system undergoes a change, the internal energy also changes. The internal energy changes by an amount du is equal to delta Q minus P dV. From the second law of thermodynamics, we get delta Q is equal to Tds. Substituting this equation, delta Q is equal to Tds, here we get du is equal to Tds minus P dV. Here U, T and P are functions of S and V. Next, the enthalpy changes by an amount dH is equal to du plus P dV plus V dP. Here we know H is equal to U plus PV, then change in enthalpy is equal to du plus P dV plus V dP. Substituting this equation du plus P dV, here Tds, du plus P dV is equal to Tds from the first law of thermodynamics, then we get dH is equal to Tds plus V dP. Here the enthalpy change is given by the equation Tds plus V dP. Next, the Helmholtz function changes by an amount dF is equal to du minus Tds minus SDT. As we already discussed, F is equal to U minus Ts, then change in the Helmholtz function dF is given as du minus Tds minus SDT. Substituting for du, we get dF is equal to minus SDT minus P dV. Then the fourth thermodynamic function Gibbs function changes by an amount dg is equal to dH minus Tds minus SDT, dg is equal to minus SDT plus VdP. So here for a hydrostatic system, the four thermodynamic function changes and the relations are given as dH, du, dH and dF and dg. Since u, h, f and g are actual functions, their differentials are exact differentials. So we can apply the mathematical theorem as we already discussed. Here dz is equal to m dx plus n dy, dou m by dou y at constant x is equal to dou n by dou x at constant y, and this is the condition for exact differential. So apply this equation in the four relations, we get du is equal to t, first relation du is equal to t ds minus p dv. Here in the place m is here m is equal to temperature T, then n is equal to minus p, here y is equal to y. Comparing this equation with this, then we can replace all the functions from this, and we get minus p, and here x we get s, then y equal to v. Applying this equation here, dou m by dou y at constant x, here m t, then dou t by dou v at constant s is equal to minus of, here n is equal to minus p, that is the sign negative there, then minus dou p by dou s at constant v. Similarly, second equation dH is equal to Tds plus Vdp, applying same rule here, then here m is the temperature, n is the volume, then dou t by dou p at constant s is equal to dou v by dou s at constant p. Then third Maxwell's relation, dF is equal to minus SDT minus P dV, here m is equal to minus s and n is equal to minus p, negatives and cancel. So we get dou s by dou v at constant t, here y is equal to v and x is equal to t. then Yx xy Vt Tv. Dou S by dou V at constant T is equal to dou P by dou T at constant V. Then fourth, dg is equal to minus S dt plus V dp. Applying same rule, dou S by dou P at constant T is equal to minus dou V by dou T at constant P. These four relations are known as Maxwell's thermodynamic relations. Next, the change of phase. The Gibbs potential per unit mass in one phase is equal to that in the other, whatever the value of pressure be. This means that the pressure changes, the temperature as well as the Gibbs potential for the two phases changes. Then the values of Gibbs potential for two phases at pressure P and temperature T is taken as G1 and G2. Then at pressure P plus dP, when there is a change in pressure, we taken as P plus dP and temperature T plus dt, the Gibbs function become G1 plus dG1 and G2 plus dG2. Then as I already mentioned, for a phase transition, the Gibbs function remains constant. There will not be any change in Gibbs function. So, a phase transition, G1 is equal to G2 for a given pressure and volume, given pressure and temperature, and G1 plus dG1 is equal to G2 plus dG2. Subtracting these two equations, we get dG1 is equal to dG2. Here find dG1. Here dG1 is the differential of Gibbs function. Here dG is already given as minus S dt plus V dP. Then dG1, for dG1 is equal to minus S1 dt plus V1 dP. Then dG2 for second Gibbs function minus S2 second entropy plus V2 dP. Comparing these two equations, dG1 is equal to dG2, comparing these two equations, we get minus S1 dt plus V1 dP is equal to minus S2 dt plus V2 dP. Then S2 minus S1 becomes into dt is equal to, taking V1 dP into this side, V2 minus V1 into dP. That is dP by dt is equal to S2 minus S1 divided by V2 minus V1. S2 minus S1 is the change in entropy of the system, and S2 minus S1 is given as delta Q by T. This is from second law of thermodynamics. So, T is equal to a constant. Delta Q is known as latent heat L at the transition temperature. And this famous equation, here dP by dt is equal to L by T into V2 minus V1. This famous equation is known as Clausius-Clapeyron equation. Thus, Clausius-Clapeyron equation involves latent heat and it is mainly useful in phase transitions. Next, the TdS equations. The entropy of a pure substance can be imagined as a function of T and V. Here we consider the entropy as a function of temperature and volume, as a function of temperature and volume. So, we write the change in entropy ds is equal to dou S by dou T at constant V into dt plus dou S by dou V at constant T into dV. Then multiply this equation with temperature T, we get Tds is equal to T into dou S by dou T at constant V into dt plus T into dou S by dou V at constant T into dV. Since Tds is equal to delta Q for a reversible process, it follows that's from this equation. T into dou S by dou T at constant V can be written as Cv, because T delta S can be written as delta Q. Delta Q at constant volume. Here volume remains constant, then the quantity of heat absorbed at constant temperature is equal to Cv, and it is given as specific heat of gas at constant volume. Then this dou S by dou V at constant T. This is from Maxwell's third relation. Maxwell's third relation gives dou S by dou V at constant temperature is equal to dou P by dou T at constant V. Substituting these two equations in the above equation, we get here T into dou S by dou T at constant V is equal to CV, CV dt, CV dt plus T into dou S by T here constant T, dou S by dou V at constant T is equal to dou P by dou T at constant V. Substituting, we get TdS is equal to CV dt plus T into dou P by dou T at constant V into dV, and this is known as the first TdS equation. Next, if the entropy of a pure substance is regarded as a function of temperature and pressure, here we take S as a function of T and P, then the change in entropy is equal to same procedure dou S by dou T keeping volume constant into pressure constant into dt plus dou S by dou P into T into dP. That is, here pressure remains constant, here temperature remains constant. Then multiply this equation with T, TdS is equal to T into dou S by dou T at constant P into dt plus T into dou S by dou P at constant T into dP. Then this equation become, as I already discussed, T into dou S by dou T at constant P, here constant pressure. So, it's become Cp, specific heat of gas at constant pressure, and this relation dou S by dou P at constant T comes in the Maxwell's fourth relation. So, applying Maxwell's fourth relation, we get dou S by dou P at constant T is equal to minus dou V by dou T at constant P. Substituting these two equations in this, we get TdS is equal to Cp dt minus T into T here, minus sign here, minus T into dou V by dou T at constant P into dP, and this equation is second TdS equation. These two equations are very important in some particular cases of chemical reactions. Let me conclude the session. In this section, we have discussed the four basic thermodynamic functions, then famous Maxwell's thermodynamic relations, the Clausius-Clapeyron equations, then the change of phase, then Gibbs function, how this Gibbs function remains same in this phase transitions, and so on. So, hope the session was beneficial for you. See you next time. Until then, goodbye. Take care.